Section 6.6 is about iterative methods for linear systems. The first question you would ask is, why bother with iterative methods when we have a Gauss elimination that gives the exact answer to round off error within a finite number of steps? Why bother with an iterative method that only gets closer and closer sometimes to the solution? The answer is that for certain large sparse problems, sparse means mostly zeros in the matrix, certain important applications, iterative methods may be a lot faster. They're not the kind of examples we're going to do in here. They're not really appropriate for you 4x4 linear system. You're probably going to just use Gauss elimination and get the right answer and don't worry about convergence and so forth. So these iterative methods are basically for certain types of applications where you have really large systems, and Gauss elimination takes a while, and iterative methods may or may not be faster. So we're still solving x equals b like the rest of this chapter, but now we're going to divide a into two parts, n and minus p, where what we choose for n will determine what method we're using, but just to divide the matrix into two parts and keep the n on one side and take the px on the other side, and then you iterate with that. So put in old x vector here and calculate new vector x in k plus 1. And of course that assumes that it's easy to solve n x equals something, because you have to actually solve a linear system here. So if n is a full matrix, it's probably not going to do any good, because every iteration will be as much work as solving the original system. But typically n will be, in our two examples, will be the diagonal part of A or the lower triangular part. And in both cases, it's a lot quicker to solve this than to solve the whole system. So n needs to be easy to solve. So that's your iterative method, and this is the general theory. We'll have two methods, Jacobi and Gauss-Seidel, where we have different choices for n. Well, I'll go ahead and tell you that for the Jacobi method, n will be the diagonal part of A, and for Gauss-Seidel, it will be the lower triangular part. So subtract these two equations. This is the equation satisfied by the exact solution x. X is the vector of the exact solution of ax equals b, which is equivalent to this. And here's your iteration. Now you subtract the two and you get e in ek plus 1, where ek plus 1 is xk minus x, the error after k plus 1 iterations. Ek is the error after k iterations. The b's cancel out and you get p e to the x. So n e to the k plus 1 equals m ek, and therefore ek plus 1 is n inverse p ek, where we call n inverse p m. So the error vector each step is multiplied by matrix m, where m is n inverse p. So after k iterations, the error is just m to the kth power times the first error vector. Now it's known that the powers of m of a matrix go to 0 if and only if all the eigenvalues are less than 1. And we can prove that in the case where m is diagonalizable. In the more general case, it's harder, but let's just prove that if m is similar to a diagonal matrix, you know from linear algebra that not all matrices are, but a lot of them are. So if m is similar to a diagonal matrix, then D will have the eigenvalues of m, because D and m are similar matrices, so they have the same eigenvalues. And the eigenvalues of a diagonal matrix are, you just read them off the diagonal. So D has the eigenvalues of m. We don't necessarily know what it is, but we're assuming that it exists. Then if you take m to the kth power, you get SDS inverse k times. That's everything. The s's all cancel except the first and last, and you get s d to the k, s to the minus 1. And a diagonal matrix to the kth power is easy to calculate. That's just the diagonal entries to the kth power. So if all the eigenvalues of m, and therefore which are the diagonal elements of D, if they're all less than 1 in absolute value, including complex ones, then as you raise the kth power, they all go to 0. So this whole matrix goes to 0 if all eigenvalues of m, i.e. all diagonal elements of D are less than 1 in absolute value. So your iterative method, you want to have M, which is n inverse P. Remember, n is the part you leave on the left-hand side, P is the part you take to the right-hand side. N inverse P needs to have all eigenvalues less than 1. Well, notice that if Z is an eigenvector of M, then any norm, this could be the infinity norm or 2 norm or 1 norm or any matrix norm of M, is defined as the maximum of the vector norm mx over vector norm x, but that's the maximum over all non-zero x. But so that's greater or equal to a particular one. If you just take the eigenvector Z as one of your x's, then the maximum of these has got to be greater than or equal to mz over z for a particular z. And if mz is lambda z, then you just get the absolute value of lambda, which shows that any matrix norm of M is greater than or equal to any eigenvalue, which means if you can prove that a norm of your matrix M is less than 1, that proves all the eigenvalues are less than 1, therefore it converges. And norms of matrices are easier to calculate than eigenvalues. So if you see that the norm of M is less than 1, we'll use the infinity norm, but it could be any matrix norm, then that guarantees convergence. However, if the matrix norm is greater than 1, doesn't necessarily mean that it doesn't converge, because all eigenvalues are less than that and they might still be less than 1. So if the way to be sure whether it's going to converge or not is look at the eigenvalues of M. Are they all less than 1? Easy way is to check the norm, and if it's less than 1, then it's guaranteed to converge, but it's not a necessary condition. Okay, now an example. Before I go into the example, a couple of things here. Notice that the B vector has nothing to do with whether or not it converges. It doesn't matter what B is. It's A that determines whether it's convergence. Well, it's n inverse P. And furthermore, the initial error doesn't matter either. That's different than nonlinear problems. It matters a lot how close you start, but for iterative methods for linear systems, it's either going to converge or it isn't, regardless of where you start. The closer you start to the solution, the sooner you'll get there. But if if the norm of n inverse P is less than 1, or if all eigenvalues are less than 1, then it's going to converge no matter how far you start or how close. So it's the matrix itself that matters, not the right-hand side or the starting value. Okay, we're going to do an example with this 4x4 linear system. This is problem 2 in the book. The Jacobi method, n is the diagonal part, as I said, and p is the everything else. This is p. So n minus p is the original a. We take the minus p on the other side as plus p here. So that's the Jacobi method, and then you just solve for x1, divide by 9, solve for x2, divide by 8, and so forth. So the new x1, x2, x3, x4 is equal to this minus these, all divided by 9, 8, 7, and 6. And if you write this out, you'll see that your M matrix, that is your new iteration, is equal to M times the old one, and M is going to be minus 1/9, minus 1/9, minus 1/9. It's this inverse times that, so basically divide the first row of this through by 9, the second one by 8, third one by 7, fourth one by 6. So there's your M matrix. Now notice that the infinity norm of this matrix is less than 1 because the sum of the absolute values of every row adds up to less than 1. That's because the original matrix is diagonal dominant. Diagonal dominant means, for a matrix, means that the diagonal entry is bigger than the sum of all the others put together in absolute value. So 9 is bigger than 1 plus 1 plus 1, 8 is bigger than, etc. 6 is bigger than 1 plus 1. Therefore, that, as you can see, guarantees that the infinity norm of the M matrix is going to be less than 1 because the denominator is bigger than the sum of all the numerators in each row, so the row sum is less than 1. So if a matrix is diagonal dominant, Jacobi method is guaranteed to converge because the M matrix will be have a norm less than 1, therefore all eigenvalues less than 1. Now if the norm of the M matrix is not less than 1, it might still converge. So we'll do an example in a minute, but basically Jacobi method, all you do is solve the first equation for x1, second equation for x2, third equation for x3, and fourth equation for x4, and put in old values here, calculate new values, put in old values, calculate new values, and keep going. And by the way, if it's clear that if these methods converge, they converge to the correct the solution. Well, let's go back to the first page here. Yeah, I should have mentioned that if this method converges, what does that mean? That means that after a lot of iterations, xk is the same as xk plus 1, and if we call that common vector x, then nx equals b plus px, which is this, which is equivalent to that. So if it converges, you don't have to worry about converging to wrong answer. It'll be the solution. The question is, does it converge or not? So Jacobi method, you just solve the first equation for x1 and so forth. And if the original matrix is diagonal dominant, then the M matrix will have norm less than 1 and everything's fine. It'll converge. Basically, it kind of seems reasonable that the diagonal elements need to be large compared to the others for this to converge. Remember, you want M to have a small norm or small eigenvalues, so you want n to be large and p to be small, so that n inverse p is small in some sense. Okay, for that same 4x4 linear system, the Gauss-Seidel method, n is the lower triangular part, so you leave the whole lower triangular part, not just the diagonal part on the left-hand side, and take the upper triangular part on the right-hand side. So now this is p, and that's n, and that's your iteration. Notice you solve the first equation for x1, then the second equation, you take the x1k plus 1 on the other side. So this is equivalent to this because I've just, so this is x1 to the k plus 1 plus 8, x2 to the k plus 1 equals all that. I just take the 1 times x1 to the k plus 1 on the other side because I already know it. See, there's k plus 1s. Looks like this is implicit because there's new values over here, but they're already known new values. In other words, after you calculate new x1, you already know that. After you've calculated new x2, you know both of these. After you've calculated new x1, x2, x3, you know all of these. So there's nothing unknown on the right-hand side, but it's equivalent to leaving everything on the left-hand side and then solving for x1, x2, x3, x4, and taking all the other k plus 1s on the other side. Anyway, this is equivalent to this. Now, what is the M matrix? Well, that's harder. You'll have to do some work to figure out what M is. And it can be shown that if the original matrix is diagonal dominant, which it was, then Gauss-Seidel is also guaranteed to converge. And usually it converges faster, which kind of makes sense because the only difference between Gauss-Seidel and Jacobi is that the Gauss-Seidel uses the new values as soon as they're calculated. In other words, if I remove the k plus 1s and change all these k plus 1s to k, this is just the Jacobi method. So Jacobi insists that I use each iteration, I use the values from the previous iteration for everything on the right-hand side, whereas Gauss-Seidel says, well, if you've got a new x1, why not go ahead and use it? If you got a new x1 and x2, why not go ahead and use it? And it makes sense that that would converge faster, I guess. And it's not at all obvious, but as I said, it can be proven that if the original matrix is diagonal dominant, which it is, the Gauss-Seidel method will also converge. Okay, now let's run a MATLAB program that does Gauss-Seidel and Jacobi method applied to exactly that system. First of all, see this A, notice it's set to 0, so just ignore it. We'll play with that in a minute, but let's suppose at the moment A is 0, so just ignore that. And B is this vector 75, 54, 43, 34, just like the book says. And your matrix A is 9, 1, 1, 1, A is 0, 1, 8, 1, 1, 1, 1, 7, 1, 1, 1, 1, 6. It's diagonal dominant. This is the true solution. We're going to only use that to calculate the error, decide when to stop. And we're going to start Jacobi method starting from 0, 0, 0, 0. As I said, it doesn't matter what you start at. It's either going to converge or it's not, independently of where you start. So Well, this is the Jacobi method. We're going to do 100 iterations of Jacobi, and we've just solved the first equation for x1, second equation for x2, and so forth. But I don't want to use the new x1. With Gauss-Seidel we will, but Jacobi I want to keep using old from previous iterations, the x's, so I calculate new x's and I call that y, and then after I'm finished I copy y to x. So this way I'm actually using old values of x, all the old values of x here, and calculating new values. And I calculate the actual error, know the true solution, and stop when it's less than such and such, and print out the final solution, how many iterations. And then I'm going to calculate some things here for Jacobi. Remember, the n is the diagonal part, p is n minus a, in other words a is n minus p, and m is the n inverse p, and I'm going to actually calculate the norm of m and the eigenvalues of m. And we know that it's going to converge if and only if the eigenvalues of m are less than 1. If the norm is less than 1, that's sufficient but not necessary for convergence, the infinity norm. Then we do Gauss-Seidel. It's exactly the same, except I don't put a y here, I use x1. So when I use x1, the second equation, that's the new x1. This is the new x1, x2, new x1, x2, x3. So this is the only difference between this and Jacobi. And I stop when the error is less than the same amount, print out the number of iterations and the final result. And then I calculate n is the lower triangular part for Gauss-Seidel, p is n minus a again, and I calculate inverse of n times p, and again calculate the norm and the eigenvalues. So let's run it. And Jacobi method takes 13 iterations. There's the correct solution. There's your the n is the diagonal part for Jacobi. M is this matrix. Notice the norm of m is 1/2. 1/6 plus 1/6 plus 1/6. Remember, norm of a matrix, infinity norm, is the maximum row sum. And the eigenvalues are all less than the norm. Therefore, since the norm's less than 1, so are the eigenvalues, so it's guaranteed to converge, and it did. Then Gauss-Seidel takes fewer iterations, 6 iterations instead of 13, converges to the true solution. This time n is the lower triangular part, and m is not obvious, but we calculated it. Now the norm of m is 1/3. The eigenvalues should all be less than 1/3, and they are, so it converges. Now I'm rerunning, and I changed a to 10. Now what does that do? Well, that just changes the element in the upper right hand corner to 11, and notice that this matrix A is no longer diagonal dominant, because now in the previous run A was 0, and so that's 9, 1, 1, 1, but now it's 9, 1, 1, 11, so it's not diagonal dominant. And I've modified B so that we have the same solution, so that's not important. So now A is no longer diagonal dominant, and let's see what happens with Jacobi and Gauss-Seidel. Jacobi still converges, even though it's not diagonal dominant. The norm of the M matrix is no longer less than 1, but all eigenvalues are less than 1, so it still converges even though the norm of the right-hand side matrix is greater than 1. So, and Gauss-Seidel also converges. Its norm is also M. The M matrix for Gauss-Seidel also has norm greater than 1, but it still converges because all the eigenvalues are still less than 1. Okay, now I changed A to 50. That means the first row of your original matrix is 9, 1, 1, 51, so it's very not diagonal dominant now. And notice that Jacobi method does not converge, at least in 100 iterations. It doesn't converge, it doesn't print out the solution, and because it didn't converge. And now the norm of the M matrix is nearly 6, and one of the eigenvalues is bigger than 1. That's why it doesn't converge, not because the norm is greater than 1, but one of the eigenvalues is greater than 1. That's why it didn't converge. Now the Gauss-Seidel did still converge in 54 iterations. And why? Well, its M matrix is still bigger than 1, but all eigenvalues are less than 1 still, so that's why it still converges.